In a recent video I covered conversion of a traditional tungsten set of lights to LED ones with a little simple resistive dropper, and the beauty of the resistive dropper was that it's super simple and it's pretty much indestructible, and as long as you use reasonable values it will last forever. You know, the resistors are one of the most robust components if they're not overrun. However, some of you are asking how can we make it run brighter, and the answer is with capacitive droppers. And by sheer coincidence, on eBay from China you can get these little LED controllers, and they're actually capacitive droppers. I'm not sure what their actual application is. I guess it's just maybe displays or something that just have the LEDs run at mains voltage. You can use these, you can repurpose them, well, not repurpose them, you can use them outright, because this is their intention, to run a string of these LEDs. And they come in different ratings, 1 to 36 pieces, 37 to 50 pieces, 50 to 80 pieces, and 80 to 130 pieces. And this is the number of LEDs you can run in series. But from what I can see, the only difference is the value of the capacitor inside. So let's take a look inside one, and then I've got another set of lights that I've already prepared to save time. And we'll modify one of these slightly, and then I shall connect it into it, and you can see how bright they look. So this is where I suddenly realised that I didn't actually prepare very well, because I know I'm going to need to make a slight modification. So I'm just going to have to rake through a tub of components here, and I've found it. Yep, that's fine. Problem solved. So inside these little controllers, they come with these shonky labels that are just like sort of hanging off. If they're not off when you get them, they'll be off soon afterwards. They just sort of fall off, they never stick on right. And inside is the stereotypical capacitive dropper like you might find in a LED lamp. So this one in particular, let's draw the schematic. It's got a 680, is that? Hold on. It's a bit blobby. 680 nanofarad, okay. So we've got the mains coming in, and there's a discrete bridge rectifier, so we've got AC in, and it's going through the classic capacitor with a discharge resistor across it. The capacitor is 680 nano, which is actually quite high. That's going to result in very high, outputs. I'm guessing it's this capacitor here that determines how many LEDs in the string are going to be run. So it's 470k, which is also pretty typical. It goes into the bridge rectifier of discrete diodes. The other terminal goes straight up to the bridge rectifier. 3 bridge rectifier, so AC in, plus, minus. Comes out the bridge rectifier, the plus goes straight to capacitor. And this is where it's going to be more suitable for American or other 120 volt countries, because the capacitor in this one is rated at 3.3 megafarad 250 volt. And our open circuit mains voltage is about 330 volts on our 240 volt supply, which means that if you unplug an LED from the string to change it, the voltage across this is going to float up to in excess of the voltage rating. It's also got a 470k resistor across it. So I'm going to change that capacitor. I'm going to change this one as well for a lower value, because that, actually, you know what, I'll leave it at its full value, because it is rated 400 volts, and we'll see what's that current that passes through the LEDs, but that's going to be very bright. So let's see, we've got the output goes through a 470 ohm resistor, and then to the LEDs. Plus, minus. So very simple. That's all the circuitry that's in it. It's just a stereotypical capacitive dropper. Now, to explain, others were asking, how does a capacitive dropper work? How does this capacitor limit the current? A capacitor is like two metal plates with an insulator in between them. So that's the plate on one side, and an insulator, and then the plate on the other side. Now, obviously current can't flow straight through the capacitor because it's got that insulator in between. So in the same way that your body charges up with static electricity if you walk across a carpet, you get a charge over the surface of your body. With a capacitor, when the polarity, say this side's positive and this side is negative, a positive charge will build up on the plate on that side, and a negative charge will build up on that side. And in doing so, a small amount of current will flow, and that current gets rectified by the rectifier and puts a little pulse of energy into this capacitor here. Then when the mains polarity changes, and this is where it does require AC to work, the polarity changes, that negative energy then sort of flows back out and gets replaced with positive energy because the polarity has changed. And this side ends up covered in positive, and this negative charge. And that basically, on each half of the waveform, it's that little oscillating backwards and forwards thing is being rectified, and it just keeps pumping little pulses of energy into this capacitor and keeps it topped up. And depending on the load, the capacitor, it's almost like a glass of water, if you will, with a tap coming off the bottom, the amount of current that's flowing through the LEDs. It'll reach an equilibrium whereby the voltage on this capacitor is just slightly above, because of this resistor, above the voltage of the LEDs, because this resistor itself will add a slight voltage. Now, this resistor is quite useful in this instance because if you were messing about the LEDs and you unplugged one and the string went open, then the capacitor will charge up to the full peak mains voltage. And when you plug the LED back in again, it will suddenly discharge, from that voltage down towards the voltage of the LEDs. So in the case of that string I've got, it's about 50 volts. The capacitor in my case would charge up to 330 volts. You can see it's quite a pulse of energy would go through. It would almost, without this resistor, you'd basically be shorting the capacitor out to a degree with the LEDs. So that's where this resistor comes in handy and limits the current to a manageable sort of level of current. So I'm going to modify this. Only modification I'm going to make at the moment is this capacitor. I'm going to change it for one that can handle our peak mains voltage. It's worth mentioning the peak mains voltage, to get it, it's roughly your mains RMS voltage, say 120 volts, times 1.4 roughly, which means it's going to be 160, 170 volts. And if you left all the LEDs, if you're running this in 120 volts, you left all the LEDs unplugged, the voltage in this capacitor would go up to around about 170 volts, so that 250 volt rating's fine. However, that also limits, that means there's a limit to how many LEDs you can drive, because you want the voltage of LEDs to be a modest level under this peak voltage of 170. So in the case of, I would say you could run 40 or 50 LEDs on that, on 120 volts. In the case of the British supply, our voltage goes up a lot higher. We could run up to, but it would be pushing it. I mean, they'd light, but it would affect the intensity to a degree without changing this capacitor. On the UK supply, we could comfortably run about 100 LEDs, I should think. So there's an advantage to having the higher voltage. But anyway, let's desolder this. I'll desolder it. We'll get rid of these leads out here, and I'll solder the Fairlight leads straight in. As I say, I've pre-made one of the sets of Fairlights up. So I'm just going to use the soldering wick. It's actually easier than trying to hold the pump. I know a few have asked, why don't you use the pump, the soldering pump? I've got a desoldering pump, but I just find desoldering wick cleaner and easier. So that capacitor is just about out. And I'll clean those pads up, just get the last trace of solder off them with the wick. Last time I was struggling with the wick because it was cheap generic Chinese stuff off eBay, and it seemed to be lacking the flux. It just wasn't absorbing the solder, and this is from Rapid Electronics in the UK. It's fine. So now I'm going to form the leads of this capacitor. So I've got my positive going to that side. Let's get them the right way around. That would be a bit dramatic if I didn't. I'm just going to fold this over the board like that to form the leads, and then I'm just going to sit them in and solder that, double checking as I do that I do have it the right way around. Because, you know, no matter how many times you check, if you're absent-minded, you can just end up putting it in the wrong way around. And while it'd be quite entertaining if the capacitor exploded and blew its guts everywhere, it would be quite messy. So let's remove these leads out the wires that came with it, and I'll replace them with the actual fairy-light ones. I'll remove this out of the way because this is just can be a bit dazzling at times. And I shall put a wee spot of fresh solder on those pads, and then I'll use the wick just to clean them off completely to absorb all the last remnants of solder so that it's easy to get the wires threaded through. If I have problems poking the wires through the holes, I might just solder them straight onto the back of the pads. So it won't be too long now. That looks nice and clean. Just two more. There are unpopulated positions in this board that look as though they've been for a voltage clamping device to actually make sure the output voltage doesn't go too high. There's an image on the marking side of the screen print side of a zener, and then two resistors, which must just be to clamp down the voltage to stop it going too high. Rightio, let's get the set of modified fairlights. At the moment I could just plug this set in and all the LEDs would fail, possibly with a loud crack noise, because that's what happens when you put LEDs directly across the mains without any current limiting. As amusing as it is, it's not terribly exciting. LEDs, they just tend to blow the end off the LED. They don't explode with smoke and flames. It's disappointing, I have tried it. So let's get the mains input side done first. I'm going to crop some of these little leads. I see a lot of long straggly leads in the back of this. So the mains in is marked in and it's right next to the capacitor. So is this wire going to go through? It might just be a wee bit too thick. Oh, I think it's going to do that horrible thing where it just splays out instead of going through properly. The temptation would have been to actually drill these out just a little bit wider. That is quite a tight fit. Now the question is, I'm going to fold that one over so it doesn't pop back out again while I'm trying to get another one in. Today was, in the UK, it was November the 5th, which means the competition has now come to an end. I'll be checking the results tomorrow, once all the stragglers have got their entries into the competition for the random prizes that I've featured recently. Of course, if this is beyond about the 6th or 7th of November 2015, then that competition is long closed, but right at the moment it's still running, and nobody actually really knows exactly what the prizes are yet, because I have not told you. Just giving you cryptic clues. Okay, now this is where I have to get the polarity right. So I have marked on one end of the string, I have marked the positive and I've marked the negative with a big black dot. So This is the negative. I'm just going to make sure I don't mix the wires up. That would be really annoying if I get the polarity wrong and popped a load of LEDs. Because the gallium nitride colours, the blues and the greens, just don't like being connected the wrong way around. So this is the negative one. So it will be going in, it just says out, but by tracing it back you can take it back to the electrolytic capacitor, so this is the negative here. Yeah, that wire is just on the borderline of going in. It's just the right thickness. I think this is going to work. I haven't actually tested these LEDs, so I don't know if I've put them all in the right way or if I've made a bad connection or anything. We'll find out shortly. And where's the other end of that string? Here it is. This is the positive end. I'm going to make sure I don't tie these in some sort of random knot before I terminate the wires. That would be quite annoying. Maybe I have done it and just don't know yet. There we go. And once I've soldered this, theoretically, well, I may just tuck that into the little plastic case. Or should I just leave it out? I may just leave it out. Although it is live when I plug it in. But we'll know if there's a fault if I leave it out, because it will go bang. Oh, go on, let's just plug it in as it is then. So this should run the LEDs a lot brighter, if it runs them at all. Oh, that is quite bright indeed. That is a lot brighter than others. There is still a little bit of shimmer on that. Okay, let's see what sort of power it's drawing. Now I know that's working, I'll just pop this into a case before I stick my fingers on it. This is where I have to precariously, in fact, you know, precariously it is indeed, because if that's not fully discharged, the two bits you'd grip it by are where the positive and negative are, so that would be quite nippy. Oh, okay, so I'll just pop that in there, and we'll see what sort of current I'm getting with that 680 nanofarad capacitor. I may end up just changing that for a lower value one, but we'll see. This gets us started anyway. Looks quite neat. I would recommend, these come open so easily, I would recommend putting a cable tie around these to actually lock them shut, just in case people play with them, because kids are attracted to bright lights. It's always... So the entire string is running at about 2.6 watts, and the current through the LEDs is 43 milliamps, which is actually just a bit too ferocious, so I'm going to have to change that capacitor down. So let's see, that's a 680. I think, you know what, 680, I could put in 220 nanofarad, would be quite bright. Yeah, because that's at the moment it's running it at, even 330 would be good, but I think 220, because I don't want to overdrive these LEDs too much. They're not rated for that sort of 40 milliamp current. So I'm going to remove this capacitor. In relation to what I was describing about how this works, the value of the capacitor in the nanofarads, or microfarads or whatever, relates to the area of the plates, and ultimately the amount of charge they can hold. So in this case, by using a smaller capacitor, less charge gets transferred in each half of the sine wave. So let's clean these solder pads. Get some wick onto it. I'll just clean that one over there as well. It's designed to take different widths of capacitors. I'll chop my wick down in length a wee bit. And desolder. Clean these pads off, ready for the new capacitor. I'm cleaning all the pads Although I could theoretically get the capacitor I'm going to put in, I could just measure which ones I need to clean, but I'll just clean them all because it gives me options. And clean the last pad, then I'll go and grab a capacitor out of my components storage area, which won't take long because I can go straight to it. So I'm going to go for 220 nanofarad. (220 nanofarad, 400 volt). Yep. So in this goes. Now, what spacing? I'll go for the wider spacing. I'll just nudge that capacitor out the way a bit. And I shall solder that capacitor in and then fold it down and put the thing back together, and we'll see what sort of current it draws when I've changed it. I would guess probably about 15 milliamps-ish, which is a nice enough current. It's still a high current for the LEDs. You know, these LEDs look great even just a few milliamps. And I'll also get an indication of the whole wattage of the whole string, which will drop to probably about 1 watt, I would guess. So that's that capacitor in now. I'm just going to fold it down for neatness, stick it back together, put the lid on, and we'll plug that back in again, and we'll see what we're going to get. So that's a nice modest brightness now. It's 16 milliamps, and it's down to half a watt. So again, I can turn the light off, but you won't see it until it's adjusted. But yep, there we go. So that's much brighter now. That's more sort of traditional fairy-light intensity. I can show you the difference if I plug in the other set that are dimmer, but dimmer by choice. These are the ones with the resistive dropper. And you'll see, actually, you know, they don't look too bad. There really isn't a massive amount of difference. These ones are visibly brighter, but these ones are still pretty darn good. I still think I prefer, for the sheer simplicity, the tiny little resistive dropper in this set. But having said that, these ones are they're visibly brighter. So maybe just better suited for applications that you prefer that sort of that extra intensity. These ones also, let's see how is there much flicker? It's not too much flicker in those ones, and not, you know, if I shake them I can see a slight ripple, but it's not dramatic. With these ones it's slightly less because it's got that smoothing capacitor. But you know, as you added more and more LEDs in series, right up to say 50 on a 120 volt supply or 100 on the 240 volt supply, then that's when the ripple would be more visible, and that's when the capacitor in this little unit would actually be quite beneficial. So I'm going to hunt on eBay and see if I can find these, because they're very elusive. You know, they're cheap, they're readily available, but it's finding what they're describing them as, because they have quite odd names. I think it might be LED driver, but you know what, that covers a multitude of devices. But yeah, that's an easy modification that you can. I'd say if you're running them at 120 volts, you probably get off with using that 680 nanofarad capacitor. I'm not 100% sure. But certainly if you ended up running more LEDs up to about the 50, then definitely that would be fine. But yeah, that's a neat result nonetheless. Now the next project's going to be 100 LED string connected into one of these, but obviously I'm not going to do that project LED by LED. That would be a very long video. But yes, good result all round.